And now we are going to talk about the iterative optimization. That is another version of the k-mean clustering. So in k-mean clustering, we consider all the samples, and then according to the centers, we are going to move the samples to the centers, to the clusters, according to the distance. But now we are going to talk about the iterative method. Each time we just move one samples. Okay. Now that is when we look at the k-mean clustering. For example, we only have 3 points: x1, x2, x3. So that means we have a finite number of discrete combination. For example, x1 belongs to m1, x2, x3 belongs to m2. Another case, that is x2, x1, x3, x3, x1, x2, and so on. So that means if we are able to list all the combinations of this, to list all these combinations and then find out the cost for each one of them, and then so we know which one is the best assignment of the clusters. Yeah. So that's why we can use the exhaustive search right here to just exhaust all the combinations in order to do the assignment. And also that is the reason why we call this is the discrete optimization. But the thing is that when the number of samples is increasing, it becomes 1,000, 2,000, so and so, and then the number of combinations will become a huge number of combinations. In that case, it is not easy for us to use the exhaustive search. In that case, one simple idea is that instead of using the k-mean clustering, moving around all the samples at the same time, we are going to just simply move one sample from one cluster to another cluster to see if we are able to reduce the cost. That means move from one cluster, move one sample from one cluster to another cluster. If the cost is reduced, that means this move is a good move. Yeah. So this kind of iterative method, that is something like the gradient descent approach, and then so it is only we can only search for the local minimum but not the global. Yeah. Okay, and now I'm going to present further details about the idea for the iterative clustering method. So assume that we have many clusters. So corresponding to each cluster, say J cluster, that is from 1 to C. So we have many samples, and then corresponding to cluster 1. So this is the data set for, this is the sample for cluster 1. We have M1 right here, and then we compute the distance. Yeah, we compute the distance. That is the subcost function, subcost value for cluster 1, and then so we have samples in, this is M2. We compute the JE using this information. We will have J2, so and so. So JI, that is the sum of the distance between the samples in the J clusters with respect to the center of MJ. Yeah. So that is what we have mentioned before. And now we are going to, when we break it down, we will just find out that the cost for cluster 1 plus the cost for cluster 2 up to the cost of the C cluster. And now we propose one method, that is we randomly pick one samples from cluster I. So we have a samples right here, that is cluster I, MI, and then so we have another cluster, that is MJ. We are going to move this cluster from I to J. So that is what we propose, and then we just find out that corresponding to this cluster, the original cost, subcost, J lowercase j, and then so this is the cost before moving this samples into this cluster, J sorry, this is ji, this is g lowercase j. That is the cost of this clusters, and then j lowercase j, that is the cost of this clusters. If we are going to move one samples from I to j, we want to know how this move change the cost of ji and jj. Yeah, so this is the result. So that means once we move one sample away from the cluster I, and then we just find out that the reduce of the cost, that is this amount, ni, that is the number of clusters in cluster I, because we move one sample away from cluster I, so the total number of samples, it becomes from ni to ni minus 1. Okay, so the same applies to the cluster j, because we move these samples from I to j, so the number of samples is increased by 1. Nj, that is the number of samples in the cluster j. So ji is reduced, jj is increased. So the resultant cost, we use the star to indicate. After we remove the ji, a sample from I to j, and then these are the resultant cost after the move. Okay, now we need to think about whether this move is the right move. If the move is right, that means the before the moving and after the moving, this je is reduced. That means after we move this point from I to j, and then after moving, this je should be reduced. So the right move, that is according to this condition, if this value is larger than this value, it indicates that after moving the samples from I to j, and then this je is reduced. Okay, this is the pseudocode. I'm going to explain that later on using another slide, and then now I'm going to present the concept in this way. So just to summarize what I just mentioned, and now we have many clusters. Yeah, we have many samples. Say the grade points right here. Oh, cluster 1, cluster 2, cluster 3, so and so. Yeah, and now we focus on the cluster I. This is the cluster I. This is the cluster j. Yeah, cluster I, that is the blue, and then red, that is the cluster j. Now I'm going to randomly pick a sample. It happens to be this one. So it means that I want to move this samples from I to j, change the blue to red. So in that case, we just find out. Yeah, so we just find out that now it becomes red, and we just find out that after we move this point from I to j, this is the original subcost. So that means to calculate this subcost, for example, this is the cluster, the first cluster. This is the M1. We just find out all the distance, sum up all the distance, and then which will give you M1. The same applies to J2. So the same applies to the ith clusters. So this is the cost Ji. This is the cost Jj. So after we move this point from I to j, and then this is the change. This is the change of the cost. So ji minus this one, this must be positive, yeah, because this is the distance. So ji is reducing, and then we use ji star to denote the updated j. And then the same for this one, because we have a new point, and then we will increase the distance or increase the cost. The updated j, we use jj star to indicate the updated cost. Okay, and now before moving, this is je. So we just sum up all the distance corresponding to each subcost. So the total cost right here, that is J1 plus J2 plus J3 plus Ji plus Jj. So that is this one up to the last cluster. Yeah. But now this is before moving. We compute this cost. After moving, we are going to move a pawn from I to J. So we need to update these two costs. According to the previous slide, the updated value, that is this and that. So I'm going to replace Ji star and Jj star by these two updated value. We are going to collect the terms J1 up to Jc, put it right here. We just find out that this is just the Je. Yeah, so we are going to put it as Je and put the blue term right here, the red term right here. Now this sum up all the right hand side, it gives us the updated value of the cost Je star. Now take a look at the last two terms. Think about under what condition this Je star will be less than the previous Je. It happens only when this term is negative. That is right here. That means if the move is correct, that means this is negative. This negative will cause this to happen. The updated Je star, which is smaller than Je. Yeah, so to indicate this is the right move. So this condition, inequality, will become this condition if this blue value is larger than the red value, and then we can conclude that the move is correct. So that's why we have this condition. Yeah. Okay. Now we're going to take a look at this pseudocode. In order to run this algorithm, we need to initialize the algorithm by preparing a data set, the number of samples, that is n, and then the number of clusters, that is c. For example, c, that is 5. That means we are going to divide the samples into 5 clusters. And then now in this slide, I just say we have many clusters, M1, M2, M3, Mi, and then up to MC right here. I do not draw the samples right here, but anyway, we have MC groups. Corresponding to each group, we are able to compute J1, J2, J3, so and so. Yeah, so we just compute the distance as I mentioned before. And now what we are going to do is when we enter this line, we are going to randomly pick a samples. For example, this is the sample I pick. It could be any one. In this example, I just picked this one. To pick this one first, because I do not know which class it belongs to. So what I'm going to do is just find out which class it belongs to using the cluster centers information. That is, I'm going to compute this point, the distance between x, we have x hat minus m1, find the distance, x hat minus m2, find the distance, so and so, including mj. Yeah, now including this one. And then so we have mc as well. So this line just, it means that we are going to pick the minimum distance. In this case, it happened to be mi, so this samples belongs to this group, belong to the ith cluster. Yeah, so this I, that is this guy, because it gives you the minimum distance. And now we go to this block. This block, that is about the moving. We are going to move these samples from I to j. We do not know which is the j. Yeah, which cluster is the j. So we are trying to move this x to m1, we are trying to move x to m2, try all the combinations. So before we do this, if cluster I, that is only one single point, we are going to stop here, because if we are going to move this point to another sample, another cluster, and then we will destroy this cluster. So we do not want to do that. So if it is not a single point, and then we are going to go through this process. This process, the first one, that is we are going to compute these value. So now we assume that we move x to m1, and then we will have this row 1, because this x is from I. So you can see that we move I to j. We assume that now j, that is 1, move from this point from cluster I to 1, and then we use this formula. So this is the amount that cluster will increase, yeah, after the moving. And then we do the same, x move to m2, and then this is the amount j2 will increase, and then x move to m3, this is the amount, and j3 will be increased. Okay, and also we are going to move x to I to because we move x away from mj, we also need to compute this value, yeah, compute this value to indicate that this is the amount, the cost will be reduced from ji, yeah. Okay, so this explains why when j not equal I, and then we use this equation, this expression. When j equals I, we use this expression. Yeah. So when j equal I, that means it move away from the ith cluster. And now the next step, that is we have many rows right here. We just examine one by one. Row 1, row 2, row 3, including this row C. Pick the one which give you the minimum row j, and then we are going to transfer this x hat to the one which give you the smallest row value. For example, this one, that is we move to here, yeah, because the distance, the row value is smallest, for example. Okay, so after moving, and then we are going to recompute mi and mk. So mi, because we have 1 point smaller, so we are going to use these clusters, using this x to compute the center again. Take the average of all the samples in this cluster, all the bull points, and then the same for this one, yeah, because we move this point to here. Now there's another case. In case x hat, the row I, that is the smallest, that means we move this x hat from I cluster back to the I cluster, because this is the smallest row. In that case, it means that the best move, that is not to move, yeah, it is because this condition is not satisfied. The move is not the right move, yeah. Okay, so anyway, after that we repeat this process. If there's no change in JE in n attempt, and then we are going to stop. Otherwise, we go back to the top, pick other samples, try to move it to different cluster, and examine the row value, determine which cluster this sample is going to be moved. Okay, so now this is the iterative clustering method using the iterative optimization. This procedure, it is the sequential version of the k-means algorithm. As I mentioned in the beginning, k-means algorithm, that is, we are going to examine all the distance of all the samples, and then so we assign the clusters for all the sample at the same time. Yeah, but for iterative clustering, each time we just consider one samples. So each time we only reclassify one sample, that is the one which is going to be moved from I to J cluster. In this case, this procedure is very easy to be trapped in local minimum, yeah, because we do not consider all the situation of all the samples, yeah. So, and also when we picked the samples, different order will give you different results, yeah. So that is also explain why it is very easy to be trapped in the local minimum and the initial condition, yeah. So it is very sensitive to the initial condition. Something like the gradient descent. If you start at different point, you will end up at different result.